Alright, hello again everyone. I hope all of you are doing great. So today I'm going to be discussing the solutions to this Google online on-campus coding round, which was held today in few of the colleges. Now I did not appear for this round as it was not held in my college. So the placement at IITs mostly happened around December. So the test in my college would be held later on, but in few of the colleges Google conducted the coding round today, and I talked to my friends who gave this test, and I could gather around 5 problems which were asked today. And I don't really have exact problem statements because obviously, but I have a rough idea of what the problems are, and in a few of the problems I also have the constraints, so that is great. But I know what the problems were totally, right? So there is no doubt about that. It may be possible that a few more problems were there, but I could find only 5 of them. So yeah, I'll be discussing the solutions to 5 of these problems. In case you appeared for this round, this might just be helpful for you. And even if it wasn't, I think it would be helpful for getting an idea of what is the level of problems which are asked in a Google coding round. Also, before starting, I would just like to say that I found the level of all these problems to be really moderate and intermediate. I gave a Google coding round myself for my internships last year, and I observed that the level of that particular test which I gave was much higher than the problems which are asked this year. So I think the level of the problems asked has decreased a little bit from the last year, because I remember that last year there was a problem based on SOSDP, and there were a few high level concepts which were asked, but in this round I think everything was pretty normal. So yeah, that would be my take. The round was a little bit easier than previous Google coding rounds. Okay. So yeah, without any further ado, let's start with the solutions. So the first problem we have here is called good path. I'm not 100% sure about the names of the problems as well, but this is what my friends told me, so I'm going to believe them. So here we have a tree which is rooted at node 1, and each node is having a particular value. So we have a value assigned to each node, and we have to find the number of simple paths which start at the root. So these paths are starting from node 1, and in which the frequency of the value of any node is at least half of the length of the path. So I think the statement is pretty self-explanatory. If we are looking at a path, it starts from 1 and ends at a particular node u. Then in the path from 1 to u, the frequency of the value of any node should be at least half of the length of the path. And the length of the path is nothing but the depth of the node u, right? I remember that the length of the path in the statement that was given, the statement said that the length of the path would be the number of nodes, if I'm not wrong, but it doesn't really matter. So the length of the path could be the number of nodes or the edges, but it doesn't really matter. The problem says that the frequency of any particular value in this path should be at least half of the length of the path, right? Now, how do we solve this problem? Let's look at the solution. So also all these problems are somewhat sorted in increasing order of difficulty, right? So that might be helpful as well. And this first problem I think is like really trivial. So let's see. So problem 1, this is good pairs. So the solution here I think is pretty simple, and you don't really need to think much about it. So the solution is just a simple DFS. So you can just do a DFS, and you can maintain frequencies of all the numbers, and you can also maintain in a multiset all of these frequencies, right? So what I'm trying to say is, do a DFS and maintain the frequency. Also in the constraints you can see that the numbers are only till 10 to the 5, so you can maintain a frequency vector, or let's say you maintain a count vector, where count of I denotes the frequency of I in the path from current node to root, right? And this can be maintained using DFS. This is the basic definition of DFS. So in the DFS stack, you currently have all the nodes from root to the current node, and instead of just maintaining all those nodes, you can maintain a count array which contains the frequency of I in the path from root to node, and also maintain a multiset. So you will maintain a multiset of all these counts, right? So basically you can maintain a multiset of all these counts, and then all you have to do is, when you are at a node u, let's say, we check the largest number in the multiset, and if it is greater than the half of the length of the path, that is half of the depth, then we increment our answer. Otherwise we don't increment the answer, right? So I don't even think I need to write it out. So we just check the largest element in the multiset, and we check whether it is greater than or equal to half of the length of the path, and if it is so, we increment our answer. Otherwise we won't increment our answer. The only thing to handle here is to maintain this multiset and to maintain these counts. That is again very easy. As soon as you enter a node in the DFS, you increment the count of that node. First of all, you delete the count of that node from the multiset, then you increment the count of that node, and then you insert the count of that node in the multiset. And once you are done with the DFS operation from the current node and you are going out of the DFS, then you again erase the count from the multiset, then you decrement the count, and then you insert the count again in the multiset, right? And yeah, that is basically it. That solves our problem. Okay, cool. So now let's look at the second problem. I hope the solution to the first problem is clear enough. So second problem is find score. This is again not a very difficult problem, but the thing about this problem is that it has some prerequisite. Okay, so let's see. So in this problem, we are given a vector of n strings with each string having length k, right? So we have a collection of n strings and the length of each string is k, and the score of a string t is defined. So we have an arbitrary string t. So for any arbitrary string t, its score is defined as the number of strings in the input that have t as a prefix, right? So for any arbitrary string t, we will look at all the strings in the input and check whether t is a prefix of that string or not, and if that is the case, then we increment the score of that string, right? So the score of a string is basically the number of strings in the input which have that particular string as a prefix. So the task that we have here is we have to find the sum of scores of each prefix of each string, right? So there are going to be k prefixes of every string. So in total there are going to be k into n prefixes. They may or may not be distinct, obviously. So we have to find the sum of scores of each of these k into n prefixes, right? I don't really have the constraints to this problem, but I can assume the constraints to be big enough that a brute force solution is not going to work, obviously. So the solution is really simple, and the prerequisite for this problem. So the prerequisite for this problem is that you should be knowing what a trie is. So you should be knowing the concept of tries, and you just need to know the basics of tries, how to build a trie. That's it. You don't really need to do anything fancy here. So yeah, if you don't know what a trie is, it's a good idea to learn it if you want to crack a coding round of Google, I think. So let's see. So the solution goes something like this. So if you know trie, I think this problem becomes really trivial. So the solution is we build a trie and mark each node that is an endpoint of a string in the input as a special node, right? So we build this trie and we say that a node is a special node in the trie if it is the endpoint of a particular string in the input, right? And I think this is a standard practice that we do. In every trie, to denote that this is a particular endpoint, we say that this node is special. We mark a node which is an endpoint, right? And now the solution is really simple. For each node, find the sum of number of special nodes in the subtree for every node. Basically, that is going to be the answer. So the answer is going to be the sum of the number of special nodes in the subtree of every node. That is going to be our answer. And the reason for this is pretty simple, because every node in the trie basically represents a prefix of some word. It may be a prefix of multiple words, right? So every node represents some prefix, and the number of strings of which that particular node is a prefix is basically the number of endpoints in the subtree of that node. And so that is the contribution of that prefix. So we just have to count the number of special nodes in the subtree of every node and sum these values. And these counts can be computed using a simple DFS, and that will be it, right? So yeah, this is the solution to this problem, and cool. So now we can go to the third problem. So this is again not a very difficult problem. So let's see. So we have three integers n, c, d, and we have two arrays a and b of length n each, and we need to count the number of pairs I less than j, such that ai minus aj plus c is less than equal to bi minus bj plus d. Right, and the constraints as always are n is up to 2 into 10 to the 5, c and d are up to 100, although I don't see why that is relevant, and ai and bi are 10 to the 9. Okay, so yeah, this is the third problem, and let's see how to solve it. Problem C, count pairs. Yeah, okay, so the expression that we have here is ai minus aj plus c, right? So ai minus aj plus c is less than equal to bi minus bj plus d, right? So bi minus bj plus d. Now what we can do here is we can build another array. Let's say we build an array capital A, where capital A of I is equal to a of I minus b of I, right? So if we build an array like this, then the relation that we have can be the inequality that we have here can be simplified as capital A of I plus c is less than equal to capital B of I plus d, right? Sorry, this should be j. So capital A of I plus c should be less than equal to capital A of j plus d, right? So now I think this is a much simpler problem. So we have an array and we just have to find the number of pairs such that aj minus ai minus aj is less than or equal to d minus c, and I think that's not a very difficult problem. So we have to find the number of pairs I j where I is strictly less than j and ai minus aj is less than equal to d minus c. So how we can do that is again not very difficult. So if we bring aj to the other side, we will get a relation like this: ai is less than equal to aj plus d minus c. Okay, so how we can do this is we can fix j and find the number of valid i's. So we can fix j and find the number of valid i's less than j such that capital A of I is less than equal to capital A of j plus d minus c, right? So yeah, this is the solution. But how exactly do we do this? Well, for a prefix we have to find the number of elements. So for a prefix in 1 to j minus 1, so in the range 1 to j minus 1, we need to find the number of elements which are smaller than aj plus d minus c. Now there are various ways we can do this. A very standard way is to use a Fenwick tree here, and if you are too lazy to use a Fenwick tree but by chance you remember what the header files for using an ordered set are, then you can also use an ordered set. So I would personally prefer using an ordered set here. So you can just use an ordered set and find the number of elements in your set which are smaller than aj plus d minus c, and that would be it, right? So I also have a code written for this problem, so let's just have a look at that. Okay, so the code here is again pretty simple. We maintain an ordered set, and for each j we are basically fixing j. We find out the number of elements in the set which are smaller than capital A of I plus d minus c, and then we insert capital A of j into our set, and that is it, right? So that will give us the final answer. So yeah, this is the solution to the third problem. Now let's move on to the fourth problem. Okay, so here we have a tree where each node I has a value ai associated with it, as was the case in the first problem. So we need to find the number of pair of nodes I comma j where I is not equal to j such that ai is equal to aj, and for each node k in the simple path between I and j, a of k is smaller than or equals to a of I, right? So I think the statement is clear enough. So now let's see how we can solve this. Okay, yeah, so let's look at the conditions. So we have to find, so the name of this problem is special paths, right? Now let's look at the conditions. So the first condition that we had here is ai is equal to aj. We have to find the number of pairs which satisfy this relation. ai is equal to aj, and all nodes in the path from I to j have a value smaller than or equal to ai or aj, because ai is equal to aj, right? So the basic thing that we have to look for in this problem is that while considering a value ai as our candidate answer, we only have to look at nodes whose value is less than or equal to ai, right? Okay. So what I'm saying is, let's say we consider a particular value for our endpoints. Let's say this value is x. Then we only need to look at the subgraph or the forest. So obviously the subgraph is going to be forest formed by nodes whose value is less than or equal to x, right? So this is the main observation of this problem. If we are considering a value x for the endpoints, then we only need to look at the subgraph or the forest which will be found by the nodes whose value is less than or equal to x, right? So let's say for a particular tree in this forest that we have, the frequency of this number x is c. Then we should just add c into c minus 1/2 to our answer, that is c2 to our answer. And the reason for that is that any two nodes whose value is x in a particular tree are reachable from each other, and we are only considering nodes whose value is less than or equal to x, so obviously the second condition is satisfied. So for a tree in this forest that has frequency of x equal to count, we will add count into count minus 1/2 to our answer. Okay, so this is the basic solution, but the problem is not yet solved right now, and the reason for that is we still need to optimize it. The value of n is up to 10 to the 5, so we can't just simply do this. Now how we can optimize is that, so how we can do the optimization is that we can apply DSU. So we will apply DSU, but we will do it smartly. So what we will do is, we will first fix the value x, and then we will look at the subgraph formed by all the edges which connect u and v such that both u and v are smaller than or equal to x, and then we will sort these edges. So let's say let's write it down. So what I'm trying to say here is that we will look at the edges. So let's say the edges are of the form u to v. So we will look at the edges in an order sorted by max of u comma v. Okay. Now when we fix the value x, we will only look at a prefix of these edges, right? We will only look at the prefix of these edges such that max of u comma v is less than or equal to x. If we do so, then we will have a subgraph which is formed by only those nodes whose value is less than or equal to x. And now when we increment the value of x, we just need to look at a few more edges, and then we will add that to our DSU. And using that DSU, we will look at all the nodes which have a value equal to x, and we will see which of them belong to the same component and which of them belong to different components. So for any two nodes which belong to the same component and have a value x, we will increment our answer by 1, right? So I think this is not a very difficult thing to understand, and this is how we are going to go about this problem. Now we will look at all the edges in the order sorted by u to v, and for a value x, we will only look at the prefix of these edges, and then when we increment the value of x, then we will add some more edges, and we will keep adding some more edges until we have taken into account all the edges, right? I also have a code written for this problem which will make it much more easier to understand for you guys. So let's see. So this is how it goes. So first of all, I'm taking in all the edges into a vector, and then what I'm doing is I am also having a map which maps from value to the nodes. So it is a map from an integer to a vector, and for each value it stores basically which are the nodes which have that particular value, right? And then for each edge, what I'm doing is in the ADJ of max of AU comma AV, I am basically pushing back this edge. What this means is that the maximum value of the two nodes which this edge connects is a max of a of u comma a of v, and in the adjacency list of that I have this edge u comma v. So now when I'm looking at a particular value, I will look at the adjacency list of that value and all the others before it, right? So I hope this is clear enough. So then I am initializing the DSU, And then since this ADJ is a map, it will look at all the values sorted in increasing order, right? So when I just iterate simply on the map, I'm basically iterating in increasing order because it is an ordered map. Now cur_val will be x dot first, which will be the current value, which is basically the fixed value of the starting point and the ending point. And then basically we are looking at all the edges which have this particular value as the max value. And then we apply our DSU and make a union of both the nodes which are connected by any of these edge. And then basically what I'm doing is I am looking in the vector vals of cur_val, which means I'm looking at all the nodes which have the value equal to x dot first. And then I am trying to find out their parent in the DSU, and I am incrementing the count of that parent. And then I can simply just go to the count vector, and I can say that y dot second is basically the number of occurrences of x dot first in a particular tree of the forest. So I will simply add z into z minus 1/2 to my answer, because any two nodes which have a value of x dot first and are reachable from each other are good, because I'm only looking at the subgraph of the nodes which is formed by values less than or equal to x dot first, right? So I hope this makes sense. So this is the solution of the fourth problem. Now we'll just have a look at the fifth and the final problem. This is again not very difficult, but a moderately hard problem. So here we are given a string s of length n, where si is a digit from 0 to 9, and we have to find the number of ways in which we can partition it into exactly k contiguous substrings. Notice that we have to partition it into exactly k substrings, such that the length of each substring is at least m, and each substring begins with an odd digit and ends at an even digit. So these are the two requirements that we have. Basically we have three requirements, because the number of substrings should be exactly k. And we have to find the number of such partitions that exist, and we have to output it modulo 10 to the 9 plus 7. The constraints here are interesting because n is only up to 10 to the 2 into 10 to the 3. So an O of n square solution will pass here, and that is pretty much what we have to do here. So I hope the problem is clear enough. Now let's just quickly look at the solution. So we have problem 5, or maybe problem E. So the name to this problem is partition strings. Cool. Okay. So what we have to do in this problem is that we have to partition a string. We have to partition a string into exactly k substrings, such that length of each substring is at least m, and each substring begins with an even number. So each substring begins with an even number and ends at an odd number, right? These are the only two requirements that we have. Now since we notice that the constraints are small here, the first thing which comes into mind is going to be dp, right? So I will just go ahead and write the dp state that we use to solve this problem. Okay, so we will be using a 2D dp here, where dp of ij is basically the number of ways to partition the first j characters into exactly I substrings, such that all conditions are satisfied. So this is the definition of my dp. So it's the number of ways in which we can partition the first j characters of the string into exactly I substrings, such that all the conditions are satisfied. So if this is the case, then the final answer obviously is going to be dp of kn, because we have to partition all the n elements and the number of substrings that we want is k. So this is going to be our final answer. The only thing that is left is to look at the transitions, and let's before looking at the transitions, let's make a very simple observation. Okay, so the main observation here is that if we look at the second condition, every string should begin at an even number and should end at an odd number, right? So the question that you should ask yourself is which particular indices are valid endpoints of a string, or maybe which particular indices are valid starting points of a string. So which indices are valid endpoints of any substring? So as you can notice, the answer is pretty simple, that each string should end at an odd character. So if a particular index I is a valid endpoint, then s of I should be odd for sure. But another thing to note here is that once we end at I, we are starting our next string from I plus 1. So s of I plus 1 should be even as well, right? Because every starting point should be an even number. So the two conditions for any point to be a valid endpoint of a substring is that s of I should be odd and s of I plus 1 should be even. If that is the case, then that particular string is a valid endpoint, right? So I is less than n, obviously. I is less than n, s of I should be odd and s of I plus 1 should be even. If that is the case, then we can end a substring here and we can start a new substring from I plus 1. Cool. Now, how do we make transitions? So let's say we are at dpij and we want to calculate the number of ways in which we can partition the first j characters of the string into exactly I substrings. So what we can do is, first of all, we will iterate on the last character of the I minus 1th substring. So since there are I substrings, I can iterate on the last character of the I minus 1th substring, right? So what are the conditions that it should satisfy? So let's say that the indices where si is odd and si plus 1 is even are special. So let's say such indices are special. Okay. So for a index to be a valid endpoint of the I plus 1th of the I minus 1th substring, the conditions are that an index k should be special. But another thing that we are missing here is that the length of each substring should be at least m. So we need to make sure that the length of the ith substring should be at least m. And so basically I minus m should be greater than or equal to k, right? That means k should be less than or equal to I minus m. Why? Because I am ending the ith substring at position, so this should be j, sorry. I am ending the ith substring at the position j, and the length of the ith substring should be at least m. So basically k should be less than or equal to j minus m. Okay. So what we have to do is dpij is basically only, so it's just the sum of all the dpi minus 1k for every valid k. So it is sum of dpi minus 1k for every valid k. And the definition of a valid k is that any special index in the range from 1 to basically j minus n, right? So this is it. We need to sum up all the dpi minus 1k values for all the special indices in the range from 1 to j minus n. Now the problem here is that if we just try to do this naively, then this would lead to an O of n cube complexity, because we already have n square states, and if we naively iterate for all the indices k in 1 to j minus m, then the solution will become O of n cube. Now we somehow need to optimize this solution, and the way we can optimize is using prefix sums. So the way we can optimize this solution is using prefix sums, right? Prefix sums. Now what is prefix sum basically denoting? So what we can do is we can maintain another 2D array prefix sum of ij, where p sum of ij is basically the sum of dpij for all special indices k in 1 to j, right? So this will basically store the sum of all dpij values for all the special indices in the range from 1 to j, right? So if we maintain this prefix sum, then our transitions become very easy. So the transition simply becomes dpij is equal to prefix sum of I minus 1 j minus m. That is it, because prefix sum of I minus 1 j minus m will denote the sum of all dpi minus 1 j's, where the value j is from 1 to j minus m, and it is also a special index, and that is exactly what we want. So now once we maintain these prefix sums, we can simply maintain these do these transitions as dpij is equals to prefix sum of I minus 1 j minus m. And once we calculate all the dpij's, we have to recalculate all the prefix sums, but that is okay, because that will be in a separate loop, and that won't affect the time complexity, right? So yeah, this is the entire solution to this problem. I also have a code to this problem, so let's just have a quick look at that if you want more clarity. So what I'm doing here is I'm initializing a DP array and a prefix sum array first of all, and then I'm converting the string to a vector because that is what I like. And then first I am making sure that I calculate which indices are special. So a special indices is one where AI mod 2 equal to 1 and AI plus 1 mod 2 equal to 0. And then I basically first calculate all the dp1i values because they are trivial to calculate. So if a1 mod 2 equal to 0 and ai mod 2 is equal to 1, then dp1i would be 1, obviously, because dp1i is basically the number of ways to partition the first I characters into one segment, and that is possible only if the first character in the segment is even and the last character is odd. Okay. And then we also do maintain our prefix sums. So prefix sum of 1i would be prefix sum of 1i minus 1 first of all, but if I is a special node, then we will also add dp1i. Okay. So this is how we maintain dp and prefix sums. Now we just have to calculate all the dp values, and for that I will first of all iterate for k from 2 to k. So I goes from 2 to k and then j goes from 1 to n. So if j minus m is less than equal to 0, obviously dpij would be 0. Otherwise dpij is going to be prefix sum of I minus 1 j minus m. And then I can just simply recalculate all the prefix sum values similar to the way we did here. Okay, this is exactly what I'm doing here. And then the final answer is going to be dpkn. Cool. So this pretty much works. Right. So yeah, this completes the solution to the last problem, and this finishes all the 5 problems that I had in mind today. So thank you so much for watching, and I will see you in the next one.